All right, let's go ahead and get started. So when we talk about types of solutions, we're talking about now a solution again is where you have a solute and dissolved into a solvent. So you can have a few different versions of that solution. So one type would be a saturated solution. So in a saturated solution, the solvent has as much solute dissolved in it as possible. So you can't dissolve anything more. Um, and really what's happening is you have an equilibrium. So some solid is still present, and then some is in solution, but that's going back and forth. So some solid will actually go into solution while some that's dissolved will precipitate back out, but it's this constant back and forth, similar to like vapor pressure, where it's constantly kind of back and forth, but the overall equilibrium is this certain amount, specific amount is dissolved. Another type of solution would be an unsaturated solution. And this is where you have less solute dissolved than what the solvent can dissolve at that particular temperature. And a supersaturated, which we went through in class, is when you have the solvent holds more solute than is normally possible at that temperature. And these solutions are unstable, as you saw in class, where I simply dropped a crystal directly into it, or a seed crystal, and then the whole thing just kind of crashed out of solution, and then the whole test tube had the solid form. So as we move to section 3 in this chapter, we're looking at the factors that affect solubility. What are the things that cause things to be more or less soluble? So using the phrase "like dissolves like" is a great defining phrase that helps us figure out, well, is this going to dissolve in a polar solvent or a non-polar solvent, and why? So what like dissolve like means is just that polar substances tend to dissolve polar solvents, and non-polar substances tend to dissolve in non-polar solvents. So basically, the more similar the intermolecular attractions, the more likely one substance is to be soluble in another. So if something has lots of hydrogen bonds, then a solvent that has lots of hydrogen bonds will also dissolve that thing. And if something has a lot of dispersion forces, then something that has lots of dispersion forces is going to be most likely the thing that will dissolve it. So if you think of glucose, which has hydrogen bonding, it's very soluble in water, while cyclohexane, okay, which only has dispersion forces, is not soluble in water. It is it's a non-polar substance. And so, although very similar in structure, if you look at the two images there, because there is no hydrogen bonding, those oxygens aren't present, like it's still a ring shape and all this stuff, it is not soluble in water because there is no hydrogen bonding, where water does have hydrogen bonding. So you would expect cyclohexane to be like soluble in like oils and other like non-polar solvents. Now vitamin A, on the other hand, which is this structure below, is soluble in non-polar compounds like fats. So vitamin A, like when you consume vitamin A, it is absorbed into like fatty tissues, or yeah, and is utilized in those parts of your body where oils and fats are present, where vitamin C, which your body also needs, is soluble in water. So it's going to go into the bloodstream and access parts of the cell that are water-based. Now let's look at how gases might behave in solution versus other things. So in general, the solubility of gases in water increases with increasing mass. So the heavier the gas molecule, the more soluble it will be in water. Now, large molecules have stronger dispersion forces. Now, when you think about solubility and pressure, so if I have a liquid and a solid and I want it to be more soluble, me pushing on it and increasing the the pressure in the environment is not going to do much as far as the solubility of that solid in the solvent. But for a gas, on the other hand, the solubility of gases in a liquid are directly proportional to the pressure. So the higher the pressure, the more the gas is going to be soluble in water or in a solvent. And if you think of like a soda pop, so the example on the right there, the reason why you have lots of carbon dioxide dissolved in that solution is because it's under higher pressure, and so all that carbon dioxide will stay in solution until you open the cap, and then the solubility, the pressure of the environment changes, and all this gas, which was soluble just a moment ago, is now coming out of solution because the pressure is not high enough to keep all that carbon dioxide dissolved in there. Well, this page also has, so we also have Henry's law, which is Sg equals K times Pg, the little g representing whatever gas you're specifically talking about, and S is the solubility of that gas, K is a constant, and it has to be specific to the solvent that you're using. Specific to that solvent and specific to the gas, and P is the pressure, the partial pressure of the gas above the liquid. So it, it might be, carbon dioxide might be different than methane as far as its solubility in water or an oil or benzene, you name it. All right, today in class I talked just a little bit about how the solubility of a substance is dependent on the temperature. So as the temperature increases, the solubility of a solid solute increases. The only one that breaks that rule is the what? Cerium? Is that selenium? Ce. What's Ce? Looking at my periodic table. I think it's celerium. We'll hope so. Anyway, so that substance on the bottom has kind of a odd solubility compared to the other solids. But for the most part, if you increase the temperature of a solvent, more solute will dissolve in that substance. Now for gases, it's totally opposite. So if you think of like, if you had the reason why we store sodas in cold temperatures, one of the benefits is that when you open it, not all the carbonation just rushes out. One of the reasons why you get more carbonation when you start drinking a beverage is that the beverage heats up in your mouth, making the solubility of the gas that much lower, and so the gas escapes out in your mouth and you get kind of that carbonated beverage taste. Now, how does this also play out? This actually has a significance when you think of aquatic environments, because oxygen is necessary for life to exist, both on land and in the water. But for organisms to get oxygen that live in the water, the oxygen has to be dissolved in the water. And so as the temperature of water increases, less oxygen is available for those organisms. So there are a lot of, so if you think of fish that live in cold water rivers and streams, like mountain rivers, so trout are a really good example of, they demand a lot of oxygen. They need a lot of oxygen to just breathe. And so when you clear cut a forest along a riverbed or along a stream up in the mountains, you remove the shade that might cool down a stream that's going through. And so as the shade goes away, the water temperature of that stream increases, making less oxygen available and making it harder for trout to survive. And then if you think of other parts of the country, so maybe like Mississippi, the South, so think of rivers where like catfish live. Okay, catfish live in warm water environments, and basically they demand less oxygen in their breathing environment, and so they survive in parts of like the Mississippi and other parts of the world in warmer climate where other species of fish might not be able to access enough oxygen because the water temperature is too high. And so that's just something to consider, like when you think of like climate change, and as the environment, as atmospheric temperatures rise, lake temperatures, river temperatures start to increase, even ocean temperatures start to increase, and that's going to change the chemistry of dissolved gases in those environments. All right, so that's where we're going to stop today, and I will see you in class tomorrow.